Hello everyone. In the beginning of the class, let us look at new announcements. Okay, the first new announcement is May 9th, 2022. Class videos uploaded. Hello everyone. I have uploaded the class videos on May 9th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the next new announcement is the slides of Chapter 3 has been updated. Version 2022-0511. Hello everyone, I have uploaded the latest version of the slides of Chapter 3 to the eCourse 2 website. The location and the file name are eCourse 2 website. Multiple input, multiple output techniques for wireless communications. Course content. Slides. Chapter 3. Slides 2022-0511.pptx. Best regards, Wei Zhen. Okay, next, let begin. We continue the class progress. Okay, let us see. Okay, a user whose name is Apple Pie. Okay, ask a question on the YouTube website. Okay. Below our MIMO course video, okay, 2022-0321 part 3. Okay. He or she asked, I am wondering, do Euclidean norm and Frobenius norm have the same meaning? Okay, this is my reply. Okay. I will answer your question in the class as soon as possible. Okay, so let us see the blackboard. Okay, because I do not have a blackboard with me, so I use the Microsoft Word instead. So the question is, do Euclidean norm and Frobenius norm have the same meaning? Okay, this is my answer. According to section 1.9.1g, the Frobenius norm is defined in one of two ways. We denote the Frobenius norm of a matrix A using the two nomenclatures below. Okay. So first definition is the Frobenius norm of A is defined as summation I summation j, the absolute value of aij. Okay, this is equation 1. And the second definition is the square of the Frobenius norm of A is defined as summation I summation j and the square of the absolute value of aij. Okay, this is equation 2. Okay, then according to 1, okay, let us see a reference 1. The reference 1 is the norm mathematics item of the Wikipedia, okay, the free encyclopedia. Okay, on the n-dimensional, okay, sorry, okay. Okay, nothing. Okay, on the n-dimensional Euclidean space r to the power of n, okay, the intuitive notion of length of the vector x which is equal to x1, x2 to xn, is captured by the formula. Okay, so we can say this is the true norm of x is defined as the square root of x1 squared plus 2 plus xn squared. Okay, this is the Euclidean norm, which gives the ordinary distance from the origin to the point x, a consequence of the Pythagorean theorem. Okay, compare equation 1 and 3. Obviously, they are not the same. Okay, let us see equation 1. Okay, equation 1, the Frobenius norm is defined as the summation of the absolute value of all elements. Okay, and in equation 3, the true norm is defined as the square root of the summation of square of every elements in X. Okay, so you can see that in equation 1 we do not have square, and we do not have the square root also. And the Frobenius norm is defined on a matrix, and the true Euclidean norm is defined on a vector. Okay, and compare 2 and 3, they are not the same neither. Okay, let us see equation 2. Okay, the square of the Frobenius norm is defined as the square of the summation of square of the absolute value of each element. Okay. However, in equation 3, we can see that the true norm of a vector, in equation 2, it does not have a square root, and in equation 3, we do not take the absolute value. So, and on the other hand, in equation 2, the Frobenius norm is defined on a matrix A, where A can be a complex matrix. So we need the absolute value here. If A is a real matrix, then we do not need the absolute value here. And in equation 3, the Euclidean norm is defined on a vector x, and x should need to be a real vector. It cannot be a complex number. So after comparing equation 2 and 3, we can find that the Frobenius norm and the Euclidean norm are not the same. This is my answer. So apple pie, if you have any further questions, please let me know. Thank you. Next, let us see the progress of the last class. In the last class, we have taught to chapter 3 slides, page 151. Please open the slides. And turn to page 151. So we are talking about, let me change the pointer. We are talking about the Meissel capacity, and in this page we consider the CSIR plus CSIT condition, which means that the receiver and the transmitter both know the channel state information. Okay, although a MISO channel has at most only one eigenvalue, okay, it can be proved using the knowledge, okay, of the linear algebra. Okay, so this is left to you as an exercise. Okay, when the channel is known by the transmitter, single mode eigenbeamforming can be performed. Okay, because there is only one eigenvalue, so we only have one eigenmode. Okay, it is easy to understood. Okay, which, as we have seen, can increase the capacity even though data are being transmitted over only one eigenchannel. Okay, we have seen before the capacity of a single mode eigenbeamforming is better than the capacity of a SISO system. Okay, let us go back to the figure. Okay, figure what? Okay, this. In this figure, we can see that the single mode capacity, okay, this curve is better than the SISO capacity, okay, this curve. Okay, let us go back to page 151. Okay, next page. The capacity of a MISO system with both CSIR and CSIT is obtained by first recalling that for a MISO channel with a single eigenvalue, lambda, okay, it follows from matrix theorem section 1.9.2x. Okay, let us go to section 1.9.2x. Okay, let me see chapter 1. Okay, here. Okay, this is section 1.9.2x. Let A be an m by n complex matrix and consider the m by m Hermitian matrix A times A Hermitian with eigenvalues lambda 1, lambda 2 to lambda r, where r is equal to the rank of the matrix A times A Hermitian. Okay, it follows from the definitions of trace and Frobenius norm and section 1.9.2p that the trace of A times A Hermitian is equal to summation I is equal to 1 to r lambda I, which is equal to the square of the Frobenius norm of A. Okay, let us go back to chapter 3. Okay, so now we know that because we only have a single eigenvalue lambda, so lambda is equal to the square of Frobenius norm of H and is equal to nt. Okay, why does this term equal to nt? Okay, let us go back to equation. Okay, let us see equation. Okay, 3.3. Okay, so the square of the Frobenius norm of H prime, okay, where H prime is the channel matrix, is equal to nr times nt. Okay, where nr is the number of receive antennas and nt is the number of transmit antennas. Okay, for fixed H prime. Okay, oops. Okay, so wait a minute. So the position of the so this is chapter 1. Okay, so let me close it. Okay, and this is chapter 3. Okay, so the position of the equation number 3.3 is wrong. Okay, let me fix this problem. Okay. Okay, good. Okay, so back to the page 152. Okay. Okay, because in equation 3.3, the square of the Frobenius norm of H prime, okay, which is equal to H here, is equal to NT times NR. Okay, when the channel matrix H is fixed. Okay, now because we consider a MISO system, okay, so single input means that the number of receive antenna NR is equal to 1. Okay, so we can cancel the term NR. So finally, we have the square of the Frobenius norm of H is equal to NT. Okay, combining this equation with equation 3.38. Okay, let us go to equation 3.38. Okay. Okay, in equation 3.38, the capacity of the single mode eigenbeamforming is equal to log 2 of 1 plus rho times lambda 1. Okay, where rho is the SNR at the receiver, and lambda 1 is the largest eigenvalue of the matrix H times H Hermitian. Okay, let us go back to page 152. Okay, yields C MISO CSITR is equal to log 2 1 plus rho. Okay, original this term is lambda 1. However, we only have a single eigenvalue lambda now. So lambda 1 is equal to lambda, and lambda is equal to NT. Okay, so this term becomes NT. Okay, comparison of equations 3.48. Okay, let us go to equation 3.48. Excuse me. Okay, in equation 3.48, we see that C MISO CSITR is equal to log 2 of 1 plus rho times NT. Okay, next page. Okay, and let us go to equation 3.45. Okay. Okay, in equation 3.45, we can see that C SIMO CSITR is equal to C SIMO CSIR. And what is C SIMO CSIR? Okay, let us go back, okay, to equation 3.44. Oh, the position of the channel, equation number is wrong. Let me fix this problem. Okay, good. Okay, so in equation 3.44, we can see that C SIMO CSIR is equal to log 2 1 plus rho NR. Okay, so let us go back to page 153. Okay, shows that the capacity expressions for MISO and SIMO systems, when both CSIR and CSIT exist, have the same form, except that the Simon equation has nr in the expression and MISO has nt. Okay, next page. If we assume that both SIMO and MISO systems have the same number of antennas, okay, this means that the number of the receive antennas in the SIMO systems and the number of transmit antennas in the MISO system are the same. Okay. The capacity expressions for both systems are identical. Okay, this is an interesting result that may seem surprising at first. In the SIMO case, the transmitter cannot employ single-mode eigenbeamforming. Okay, because there is only one transmit antenna, so its capacity is the same as it is under CSIR. Okay. Okay, in the MISO case, the transmitter is assumed to employ single-mode eigenbeamforming, and its capacity is different when both CSIR and CSIT exist than it is under CSIR only. Okay, I think these two sentences may confuse you because we have four cases. Okay, let us go to a table. Okay, table 3.4 shows the capacity formulas for SIMO and MISO communication systems. Okay, we have two CSI type. That is, the first is CSIR, and the second is CSIR and CSIT. And we compare the capacity formulas for SIMO and MISO communication systems. So you can see that there are totally four capacity formulas here. Okay. So through this table, we can easily compare the capacity formulas for different communication systems under the same or different CSI type. Okay, we will go back to this table later. Okay, let us go to next page. Okay, despite these differences, the SIMO and the MISO capacities are the same under CSIR and CSIT conditions when the number of antennas is the same. Okay, let us go to the table 3.4 again. You can see that when the CSI type is CSIR and CSIT, the capacity for SIMO communication system is log 2 of 1 plus rho nr, and the capacity for MISO communication system is log 2 of 1 plus rho nt. Okay, when nr is equal to nt is equal to n, okay, the two capacity formulas are totally the same. Okay. Okay, next page. The explanation for this somewhat unexpected result is that when both CSIR and CSIT exist, excuse me. Okay, the transmitter and the receiver can both weight the signals on their respective antennas. Okay, the transmitter in the case of MISO and the receiver in the case of SIMO in response to the channel. Okay, next page. we conclude that meso and simo systems are okay, it is 25 minutes. Let us take a break.